Good morning. We are going to look at some homework problems for part of our reviews. So I think we've got midterm 4 coming up in the not too distant future. And what I'd like to do is, I think this will be useful, you guys can let me know. But what I would like to do is use today to go back through some homework examples from chapters 42, 43, and 44. That's what's coming up on midterm 4. And step through it, see how the setup looks, talk about the individual steps, and so let's do that. So I'm going to start, it's not all the homework problems, I've just picked some that I think will be maybe the most useful. In some cases it's because they're a little more challenging. They tend to be, I'm going to say the problems I'm looking at are pretty, are problems that I think are important. So problems like this could show up on a midterm. Anyway, let's go ahead and the first problem I want to take a look at is from chapter 42, looking at those early sections on nuclear reactions. And just to review some of the stuff that we've talked about. The problem, the way it's listed in the textbook, says that a proton is fired at some lithium-7. So there's a sample of lithium-7 just sitting there, and a proton beam is generated. We can generate beams of charged particles easy enough, electrons or protons. In this case, a proton is used to set off a nuclear reaction, and what we observe is that a helium-4 comes out of the reaction as well as an alpha particle. Now, as we've been talking about in class, physicists aren't I'm going to say they're not very good at charge balancing. When I was a chemistry major, everything had to be charge balanced. They wanted us in there counting all the electrons, counting everything to make sure we could account for. Anyway, I think that is very important. So we want to charge balance this, and then we want to keep track of the electron count. We want to make sure that all the electrons are accounted for. So for example, you would think from this proton, well, there's no electron attached there. The lithium has 3 electrons attached to it. The helium only has 2. And the alpha particle, by definition, doesn't have any electrons. So the electrons don't match. Now, why is that so important? Because it's really a nuclear reaction anyway. It's just the nuclei that are reacting with each other. The electrons are entirely spectators. And the reason that's important is when we do Q calculations, we want to be able to take the mass of what we started with and the mass of what we end up with, take the difference, and find out how much missing mass there is. If the electrons are not counted properly, if we don't have the same number of electrons on both sides, we'll be off. Our calculations won't match up. When I look these different nuclear or these different isotopes up in Appendix F, Appendix F is going to give me a mass assuming all the electrons are in place. So what we have to do here to get an accurate measurement for Q, or an accurate calculation, is I'm going to convert the proton into hydrogen 1 and use the mass of hydrogen 1 on this side. That'll add an electron on. And then there's 3 here, that's 4 electrons. Now on the other side, this alpha particle and the helium-4 to me looks really funny, because how do you tell an alpha particle from a helium-4? They're the same thing. And so I just turned this into 2 helium-4s. So we're going to hit the lithium nucleus with a proton, and we're going to get 2 helium-4 nuclei. But to get the masses correct, I'm going to add electrons all around, turn them all into neutral species, and then I'm set. So that's going to charge balance, and it's going to give me the correct electron count in order to calculate Q. Again, the actual reaction would be proton comes in, hits the lithium. Now there's 3 electrons here. It's not clear what happens with those 3 electrons. If the 2 helium nuclei come out at really high energy, the electrons could get left behind. Okay, so that's a more complicated, more detailed discussion. So we're going to get the Q from here. So make everything neutral. Look up all the masses. I did that. I looked up the hydrogen 1, the lithium 7, the helium 4, and wrote down the Q values, and I got 0.018624 atomic mass units. I did my 931.5 conversion into MeV, and I got 17.35 MeV. That's a good amount of energy. That's a lot of energy release. Okay, so we'll leave it at that. That's a really high Q value for the reaction. Now, in addition to the Q value, which we calculated here, what we wanted to do was ask about the potential energy barrier. So how much of an electric repulsive force, there's going to be an electric force repelling these two nuclei from each other. So a couple different ways of seeing that. Maybe the easiest way to think about this happening is that the proton and the lithium nucleus come towards each other, and as they get really close, they begin to repel, but they're able to get close enough that they just, what we call just touch. And that's close enough that the nuclear reaction can occur. So the nuclear reaction is only going to happen over very short distances. And so what we imagine, and we've done these examples before, is that there's an electric potential energy. This goes back to physics 4b, K Q1, Q2 over R, where K is the, I didn't write it down separately, K is the electric magnetic force constant. Little k is 8.99 10 to the 9th newtons meters squared per coulomb squared. Now we've been using an approximation here for Ke squared, and it's not here. I'm thinking it's going to show up on the next slide. But for the potential energy barrier, when we're using this formula, what we're assuming is that somehow the two nuclei are set up in a way where they have equal and opposite momentum, and that means right when they react, they're both at rest. Now that's a little idealized, so we're going to go back and show what a more realistic calculation might look like. For you guys, as far as if you were given a problem on an exam, just stick with this. This is a bit of an approximation, but it works for us. So it's going to give us a reasonable approximation as to what the potential energy barrier would be under those circumstances where the two objects are just slowing down and then they both come to rest right as they react. So the distance center to center of the two nuclei comes from taking the radius of the two nuclei, and we're using our nuclear radius formula for hydrogen 1. That's just the proton, and that just has an atomic mass of 1. The lithium 7 is a combination of 7 nucleons, some protons and neutrons. So we put the 7 in there, and that gives us a radius of 2.30 femtometers. So we can add those two together to get 3.5 femtometers for, that's how close they have to come. Again, measuring center to center for the two nuclei. Now, the Q values here are going to depend on how many protons there are in the nuclei. So here, the 1 and the 7, those were the number of nucleons in determining diameter. But in terms of determining Q values, those are just the protons. And so I'm going to say Z1 is equal to 1, Z2 is equal to 3. Here is a picture of kind of what's going on. And remember, we draw these as kind of spheres, but each of these individual protons and neutrons have their own wave function. We looked at wave functions for electrons that, spread out the size of an atom or molecule. If we look closely at the nucleus, then we see that the protons and neutrons there are also described by wave functions. So let's see what this looks like then. There's a repeat of the reaction and the Q value that we calculated. Here we are getting that potential energy barrier. I brought out the factors of Z1, Z2, and then I was left with Ke squared. Now K is the electric force constant, first introduced back in chapter 21. It's not Boltzmann's constant, it's not the spring constant, it's the electric force constant. And Ke squared is one of our shortcuts. Whenever I get Ke squared in a formula, I can replace that with 1.44. Those are good shortcuts to have in your notes. In this case, the units I want to use are MeV, femtometers, and plugging in all the numbers, I ended up with a potential energy barrier of 1.23 MeV. So it's a good thing there are these electric potential barriers, right? Otherwise, when atoms and molecules run into each other, the nuclei would react. That would not be a good thing if there were nuclear reactions going on all the time. So the size of the electron wave function prevents nuclei from getting too close together, and make sure that they're a certain distance away from each other. Even at high speed, they're going to repel each other. So it's difficult to get a group of protons and another group of protons into nuclei close enough so that a nuclear reaction will take place. Okay, so this is kind of what you're responsible for, but I wanted to look a little deeper about what's happening here in terms of the U that we calculated here, the potential, the nuclear, not the nuclear, but the nuclei electric repulsion based on an electric force between the protons, is in what we call the center of momentum reference frame. Again, it's that frame where the two objects are coming in with equal and opposite momentum, and then they slow down and just stop, and then they react at rest. Now, we said that's probably not what's happening here. Probably it's a target of lithium, and there's a proton beam, and it turns out that requires more kinetic energy. This is kind of the least amount of kinetic energy that we would need, and we're going to go ahead and calculate those. So using our formula, remember our kinetic energy formulas from special relativity, when something was decaying, well, this is like a decay in reverse, right? So instead of two objects, instead of starting with one object and having it decay into two, we have two objects that are coming together and combining into one. So that one object that we combine into would be the combined mass of the hydrogen and the lithium. So combined, that would be 8 atomic mass units. Now the pieces that are coming together for that are the hydrogen, which is 1 atomic mass unit, and the lithium, that's 7. And so I'm just using these formulas. This, back in special relativity, when we defined this, these were Q's, but now since we're thinking of this in reverse, we're going to put that as the potential energy barrier. Okay, so we can use the same formula. And then I just put in the M naughts and the M1s and the M2s and follow the recipe from the formula. And it says that, what does it say here? 8 minus 1 is 7 plus it's 14, 7/8. So 7/8 of the kinetic energy needs to be in the hydrogen, and 1/8 of the kinetic energy needs to be in the lithium in order to make use of this 1.23 MeV. So it's a little idealized in terms of the potential energy barrier, or more specifically in terms of how much kinetic energy each nucleus would need to have coming into the reaction. So what we can do then is we can go, okay, well, what are the speeds going to be like? And I went back and did the whole special relativity thing. I solved for gamma using 1 plus kinetic energy over mass. Now for the hydrogen, the kinetic energy that we solved for on that previous page, 1.076 MeV of the kinetic energy is in the hydrogen. And to divide through by the mass of hydrogen, I need units to cancel here. So atomic mass units won't work. I have to get those converted into MeV, but I know how to do that. I can use the 931.5 conversion. So in the denominator now, I have the 931.5 MeV conversion, and so that final answer will be in MeV. And I ended up with, well, I ended up with this for gamma, 1.001155. When I did the same thing with the lithium, now I've got 7 atomic mass units, and again I can use the 931.5. So this is also a good example to think about, because there's a certain amount of flexibility we have now in converting back and forth between traditionally mass units of atomic mass units and energy units. Okay. So the gamma for the lithium needs to be 1.00165. I solved for the V's using special relativity formulas that we've developed. The hydrogen needs to be moving at 4.8% of C, and the lithium needs to be moving at 1.82% of C. So you can see how difficult it would be to set up this exact situation. I would need things traveling at these particular speeds. Now what we can do, now that we have the speeds figured out, is say, look, what if we imagine this happening in a different reference frame? What we can do is determine when the reaction happens, what's the relative velocity between these two nuclei. And so the relative velocity between these two would then be 0.0662 times c. So I'm going to use that as a relative velocity. And then for the center of momentum frame, what we're going to say is that the hydrogen and lithium are coming together at these velocities. In the target projectile frame, the hydrogen is coming in towards the lithium. Okay, so they are going to agree with each other as far as what the relative velocity will be for the two of them. And so what that would give us is a gamma value. Now I'm going to move entirely into the frame of the lithium. And so the lithium is now at rest, and the hydrogen nucleus is coming towards it at 0.0662 times c. So we've moved into this other reference frame. The gamma value for that is 1.0022. So putting that in and solving for the kinetic energy of the hydrogen, it says actually the hydrogen, or the proton coming in, would need a kinetic energy of 2.05. So you can see that the target approach is more realistic. But in order to get this reaction to set off using the target, kinetic energies of 1.23 are not going to be enough. We're going to have to go quite a bit higher. We're going to have the proton, or the hydrogen, coming in with a kinetic energy of 2.05 MeV. Okay. And I have, well, I'll just leave it at that. I was going to say we have not used the special relativity velocity addition formula. I think that's going to be a small correction to what we've done here, but I should probably go back and double check that also. But this is giving us a better estimate as to what the kinetic energy would actually need to be. And again, you guys don't have to do all this for the midterm. You're not going to be asked in this detail, but it's a good example to work through. It's a good review. It's a way to think more broadly about some of the other types of problems that we've looked at. Okay, and then finally, here is a reaction profile. So we've done these two. We're starting out with hydrogen and lithium that has a certain mass, and the mass is going to be reduced, and Q is telling us the difference in the masses. And so Q is Q, whatever reference frame we work in terms of. The masses before and after are going to be the same in either case. And then there's a reaction energy profile. Here is the kinetic energy of the hydrogen coming in. So assuming the lithium is at rest, and all the kinetic energy coming in is with the hydrogen, we're going to have that 2.05 MeV barrier, kinetic energy barrier that we're going to need to get past in order to have this reaction take place. All right, let's move on to another example. That was actually kind of involved. We did kind of a fair amount of detail on that one. Here's another nuclear reaction. Again, we're starting off with a proton, and the proton needs to get converted and into a hydrogen. Now the neutron doesn't. The neutron is already neutral. There are no, when I look up the mass of the neutron in the back, I'll just get the mass of the neutron, which is fine. And the neutron's not going to affect electron counting. So let's see here. This is actually positively charged, the proton. When I add the electron, I've got 1 electron here and 8. That's 9 on this side, 9 on the other side. All those electrons are going to be spectators. And so we've got that part of it balanced out. Now, again, putting the numbers in here, hydrogen 1, that's the mass for hydrogen 1. Here's the mass for oxygen 18, so a less common isotope of oxygen. And then the neutron. Now, the fluorine 18 is actually they want us to calculate what that mass is. So they want us to come up with a mass value. So let's see how this would work. Now, in the problem, we can go through, we've calculated what the Q value is for this, we've converted this into, or we can calculate what the energy release is, or they've told us what the energy release is in this, and then we can convert, last time we were taking a certain amount of mass and converting it into a certain amount of energy. This time we can do it the other way around. We can say that there's a certain amount of energy, and we're going to convert that into a certain amount of mass, and say that in terms of mass, if we add this Q value on at the front, and then add it onto the mass of the two species going in, that will balance out with the mass of the fluorine and the neutron coming out. And so we've got everything else calculated here. So here is the total energy required in the reaction, and we can use that to determine what the mass of the fluorine is. So the mass of the fluorine is at 18.000938, and I have to say I did not double check that, so I need to go back and double check the mass on the fluorine. Now, how does that compare with a potential energy barrier? And I'm just going to use the estimate for the potential energy barrier. So for a hydrogen reacting with oxygen, I have Z's of 1 and 8. That gives me radiuses of 1.20 and 3.14. The combined center-to-center distance between those nuclei, 4.34. Putting all of those values in, I ended up with 2.65 MeV, and that's going to give us a rough idea of what the electric potential energy barrier would be for this reaction. All right. So a couple of those reactions. Let's move on, and here is a fission example. So we want to look at nuclear fission also, and let's talk about this a bit. This is the example that was given in the book, and so in this reaction, we got a neutron that reacts with uranium-235. And we've talked about, you know, the fission. There's like hundreds of different combinations of fission products we might get when we set this reaction off. So we're not going to get the same results, the same products each time. These are just one particular set of products that are possible. Now, going through and writing down the masses for everything here, there's the neutron going in, here are the 3 neutrons coming out. And what we find, here is the Q value. I'm taking the mass of the uranium and the neutron going in. and I'm getting the mass of the barium, the krypton, and the 3 neutrons coming out. There's the missing mass, there's my 931.5 MeV conversion factor, and the Q value I got for that reaction, 173.2 MeV, and then, you know, it's a big deal. That's a lot of energy that's being released. When we looked at radioactive decay, we were seeing in radioactive decay maybe 3 or 4 or 5 MeV of energy being released. And up to that point, that was the most energetic reaction we had encountered. But an individual fission reaction, this one that we're looking at right here, they're releasing 173 MeV. That's a huge amount of energy that is being released. And I think that's it. I think on this one they just asked us to go in and find out what the Q value was for this, and then to kind of be astonished at just how much energy that really is. All right, here is another fission example. So, and this was a little confusing to me, but we'll take a look at. I ended up answering it a couple different ways. I wasn't exactly sure what they were getting at. Anyway, what they said in the problem is they said, let's see how much energy you get out of fission compared with a chemical reaction. Something like burning coal. So you could imagine this is a power plant. And you know, coal, when we run a chemical reaction using coal, it's combining with O2 out of the air, and everything is being converted into carbon dioxide. So if everything's working optimally in a coal plant, you know, we're getting 100% conversion into carbon dioxide, which doesn't sound healthy for the planet. And so what they told us was that 1 kilogram of coal running this reaction into carbon dioxide will release provides 30 million joules of energy. So that's how much energy is available. Now, what they wanted to know was how much uranium would it take to provide that much energy. You know, it takes 1 kilogram, 1,000 grams of carbon to produce 30 million joules. So let's do this. Let's start with the 30 million joules. And then this is a conversion that I hope you guys are familiar with. What we're doing is we're going from joules back into MeV. So there I'm converting back into some numbers of MeV. And the reason for that is I want to say that each fission is releasing some number of MeV. I'm going to use the 173. So that 173 came from the problem we just looked at. So I thought, you know, maybe that's a typical amount. Now I know in textbooks like to say a typical fission reaction releases about 200 MeV, but whenever I actually calculate the Q for a fission reaction, it's lower. So I'm not sure if that 200 number, I haven't sat down and spent hours and hours trying many different fission reactions to see if some do release as much as 200 MeV. But I went with a more conservative estimate because I just did the problem before, and I got 173 for that. So the answers here I think are going to be a little different from the back of the book. So what I ended up with was I would need 1.1 10 to the 18. Now I'm calling these reactions or fissions, and for each reaction or for each fission I would need 1 nucleus of uranium-235. So that's what I did. I just said I need that many uranium-235s to come up with 30 million joules. So I thought, how much mass is that? Because that's what they're asking me in the problem. Calculate how much indicates mass. So I took this many uranium-235s, and I used the molar mass of uranium-235, and the molar mass of uranium-235 is surprisingly 235 grams per mole. And so here is the 235 grams per mole. Numbers of uranium cancel, and now I have my answer in grams, but the answer in grams turned out to be 424 micrograms. So that's less than a milligram. That is a little tiny speck. I mean, you'd really have to pay close attention to see. Uranium's pretty dense, so 424 micrograms would be a little tiny speck of uranium that you would really have to look carefully for, versus providing that much energy compared with an entire kilogram of carbon. Okay. All right, so that's, we've seen examples kind of like this. It's an enormous amount of energy per reaction, and so we just don't need very much uranium-235. Now, I solved it this way for uranium-235. When I went back and looked at the problem said how much uranium-238 would we need. So I'm not sure what they were getting at with that. It's interesting, they didn't say how much uranium-235. They also just didn't say how much uranium without identifying any particular isotope. So, uranium-238, that's the really common isotope. That's the one that's like 99.3%. And then the uranium-235 is almost the entire remaining portion. There's one more, I think, isotope, one more in there that's it's a really low abundance. And running this number, inverting this one right here, says that uranium-235 makes up about 1 out of every 139 uraniums. So if that's what they're after, is how much uranium do I have to order in order to get enough uranium-235 in order to run this reaction, then that's roughly going to boost things by a factor of about 139. Now that's not quite true, because if I need this many uranium-235s, and there's 1 uranium-235 for every 139 uraniums, but the average molar mass for uranium is not 235, it's much closer to 238. And so I should really use the 238 molar mass, and that shifts things a bit. Anyway, I ended up with 60,400 micrograms of total uranium. From that, I would be able to isolate, which would not be trivial, but from that 60,400 micrograms, I would be able to extract 424 micrograms of uranium-235. All right. So it's one of those gee whiz problems with fission. How much energy can we possibly get from these reactions? And it's a lot from a little bit of uranium. Now, we've got kind of a similar problem here, I guess. We're now, in this problem, looking at nuclear fusion, and we spent a fair amount of time in lecture going through the fusion reactions that are occurring in stars, or at least the hydrogen to helium fusion reactions. But now we're looking at some different sorts of reactions. These are going in stars also. There's kind of a mix of a lot of different isotopes present. But these reactions that start with deuterium are actually reactions that we might utilize at some point in a nuclear fusion power plant. So we tend to start with, it's very difficult to start just with protons and run those reactions where the protons turn into neutrons. The reactions are going to be easier for us if we already start with neutrons that are in place. Now, what that means, though, is if I take, what are the prominent sources of hydrogen where we could look for fuel to operate our nuclear fusion plant? And, an obvious example is, water. There's a lot of water on the surface of the Earth, and how much of that, in all the water, there's an enormous amount of hydrogen. Now, even though there's an enormous amount of water and a lot of hydrogen, deuterium within the hydrogen, naturally occurring hydrogen, is only at about 150 parts per million. We would have to sort through a million hydrogen atoms from the water in order to get just 150 deuteriums. So it's not very common. Now, that abundance, that 150 parts per million, that's a number, I was looking up some of these numbers, that applies to the water present on Earth. But, you know, maybe a little surprisingly, maybe not, the deuterium abundance is different in different compounds. So if you look at other compounds, hydrogen-containing compounds on Earth, the portion, the parts per million, varies by a fair amount. And so some of those abundances are about half this, and some of the abundances are, higher by some amount. But for the naturally occurring water on Earth, the number I kept seeing was 150 parts per million. So that's what I went with. So anyway, let's see what we've got here. This is the reaction they gave us. Now, they assume that we just look back in the book and come up with a Q value, but I went ahead instead. I went with I calculated the Q value myself. So here it is. I wrote down the mass of hydrogen 1, hydrogen 2, hydrogen 3. They're just all different isotopes of hydrogen. And then I took 2 of the deuteriums and subtracted off the tritium and the hydrogen 1 here. And it turned out that that's a pretty good energy return, 4.00 MeV per reaction. Now notice, every time we run that reaction, we need 2 deuteriums, not 1, but we need 2 deuteriums to run that reaction and release 4 MeV of energy. So I took the 1 kilogram of water. So what the problem asked was this. They said, hey, if I take a kilogram of water, a liter bottle, I don't have my liter bottle with me here, but if you take a liter bottle of water, and somehow you are able to sort out every last deuterium in there, again, not trivial, but if I can get all the deuterium out of there, how much deuterium would that be? And so I did some dimensional analysis here. The molar mass for water is 18 grams per mole of water. That's going to tell me how many water molecules I have. And then for every mole of water, I'm going to have 2 moles of hydrogen. So I'm separating off the hydrogen. And then for every mole of hydrogen that I come up with, that's Avogadro's number. And then what that 150 parts per million is equivalent to is 1 deuterium out of every 6,700. So I use that. I kind of like the 1 out of. For me, that's an easy way to think about things. So what I ended up with was 1 times 1.0, 10 to the 22 deuteriums in a liter of water. And then I did a molar mass on that. I should have showed the details of the calculation. You guys can try that. But I ended up with 33 milligrams of deuterium out of an entire kilogram of water. So it's not a lot of deuterium, but it turns out that it potentially could, even that small fraction, could provide a fair amount of energy. And notice what's also happening here is we're not using all the hydrogen, right? In fact, we're only using 150 parts per million. Most of the water can just remain water. We just want the deuteriums out, and that's going to affect only a small number of hydrogens. All right, so that's the amount of deuterium. And then I took that number of deuteriums in each liter, each kilogram of water, and said that I'm going to need 2 of those to run the reaction each time. And then I converted back into joules. So there's that conversion again. Now remember, since it's MeV, this is, the conversion factor is 1.60, 10 to the minus 13, not minus 19 joules. And what that worked out to be was 3.2, 10 to the 9th joules, and that's running a fusion reaction. So it's saying here that compared with, well, in the problem, as a comparison, they said, now compare this with gasoline. If I take kilogram of gasoline, that gasoline has 50 million joules of energy. If I run the reaction, again, producing as products here, if I react gasoline and oxygen, I'm going to get a bunch of water and CO2. Okay, so again, lots of CO2 being produced with gasoline, with a petroleum product or a fossil fuel. It turns out that just a liter of water has, if there's a way to get out that deuterium and react it, would have 64 times as much energy in it. All right, so there you go. There's an enormous amount of energy available through running these fusion reactions. Okay, and we're only using the very, very low abundance deuterium isotope for that. Okay, let's see. And then, so we looked at nuclear reactions, we looked at fission, we looked at fusion. Let's look at this last section of chapter 42, and we're looking at radioactivity and radiation dosing. And so what they tell us in the problem is that radioactive iodine is potentially a risk. What happens is this: if you've got, if you've got a good example of this, I guess, was the Chernobyl power plant in Ukraine from, it's been a while now, right? 15, 20 years ago, at Chernobyl. And iodine-131, which is radioactive, is a common fission product. So iodine gets produced in this radioactive iodine gets produced in fairly high quantities. Now the problem with absorbing iodine-131 is it gets concentrated in the thyroid gland. So if you somehow ingest some of this iodine-131 and it dissolves in your fluids and circulates, it's going to get snatched out of the bloodstream, and it's going to end up getting into your thyroid gland. The thyroid gland incorporates iodine as a hormone, thyroxine, that the body utilizes to regulate metabolism. It's kind of interesting that that element only gets used at one place, but physiologically you're able to really highly efficiently pick up the iodine and then store it in the thyroid gland. And so that concentrates it. When it undergoes radioactive decay, there's a real risk to your thyroid gland from this radioactive iodine. So you may have heard in the stories, if people were exposed to radiation released from a fission power plant, for example, or from a fission detonation, you can take iodine to bring the iodine concentrations in your body really high, and then your body will, that gets flushed out. So if the iodine gets too high, then it's going to get released. The thyroid can't take up all that iodine. So anyway, it says write down the reaction. So I did. Now it says it's beta minus decay, so that means it's going from element number 53, which is what iodine is, and so that means it's going to turn into element number 54. And I always have these underlying reactions. Neutron turns to proton, electron, and an anti-neutrino. So there's the anti-neutrino, needs a bar over it. There's the electron. I got everything labeled. And I even charge balanced, so the charge balancing is important. I'm going to make a big deal about that. So the xenon actually is missing an electron because only 53 electrons came in. That's not enough to make xenon neutral, so it's going to have effectively a missing electron. But at the same time, the reaction created an electron. Now that electron's zipping away at really high speeds and kinetic energies, it's not coming back. So the electron that gets produced through this reaction is not going to get drawn back in by the xenon. But that doesn't matter for our counting. For our electron counting, the mass of an electron that gets produced can be added to the xenon and combined to come in and get a Q value. And I think we're going to do a Q value here. There's some more parts. There's like A, B, C, D and E or something. We'll get back and get that Q value calculated. All right, so in part B, it says how much time would it take for the iodine 131 to decay down to 7% of the original amount. Oh, Laney is here today, huh? Laney's right here. All right, so the half-life for iodine, 8.02 days, and we want to get down to 7%. Let's see how much time this is going to take. Now, the way that these decays work is we've seen this as an exponential drop-off. Now, we can either do this in terms of numbers of iodine 131, or we can do it in terms of the rate, decay rates. And I think numbers fits well here. It sounds like what they're talking about more directly. So I went ahead with just counting. So of the number that we originally start with, we want 7% left. So that becomes a ratio for n naught and final n. So I took this equation, ran a logarithm through it, and ended up with this formula, t over tau equals the natural log of n naught over n, and then I just solved for t. So t is equal to the lifetime, tau, times the natural log of n naught over n, and then I put the days, I put the values in. Now, they didn't give me a lifetime directly. I was able to look up a half-life, 8.02 days, and so to convert that into a lifetime, I had to divide through by the ln of 2, and that gave me 11.58 days. Or I went ahead and converted this into seconds. It turns out it's almost exactly 1,000,000 seconds, just coincidentally. Iodine 131 has a lifetime of 1,000,000 seconds. Now, it seemed like the units I probably want to work in terms of, at least for this part of the problem, is days, so I used the 11.58 days, and then I put the logarithm of 100 over 7, that's my 7%. But notice that it's inverted. The 100 goes on top and the 7% goes below, because when I solved it, there was a minus sign right here, that in order to remove that, the logarithm is in terms of n naught over n. So I eliminated the minus sign and this flipped over, and that's why it's 100 divided by 7. So when I calculated this, it came out to be 30.8 days. So that's our number. For how long would it take to drop down to 7%? Okay. Now in part C, it says that a sample of radioactive iodine 131 that was even what's called 1 millicurie would be enough to potentially be, it would be a health risk. Potentially it could be lethal. So we're saying that how much iodine could we, how much of this iodine 131 could we tolerate? And if it's only 1 millicurie, I don't know if you guys remember, but curies are like the weirdest units ever. First of all, Ci doesn't sound like curie to me. I guess you can't use Cu because that looks like copper. And then the number is also kind of funny. A curie is defined as a sample of something radioactive that decays at a rate of 3.7 10 to the 10th seconds. So it's actually a measurement of how rapidly your sample is decaying. And that always felt a little unnecessary to me. So whenever I get a problem, and they show up, you see these in the book, I just get rid of the curies and immediately convert that into decays per second. So let's say that we have a sample of radioactive iodine 131, and the sample size is such that I am measuring 3.7 times 10 to the 7 decays every second. All right, and they're saying that if you have a sample with that many decays of this particular isotope, it's going to be harmful. So they wanted us to find out how much mass that corresponds to, and yeah, that makes sense to me. In fact, maybe that's what we should have started with. In any case, what we can do is use our formulas that we've developed. We can take the rate, multiply it by the lifetime, and just count how many iodine 131s we have, which I always feel like is more useful. Forget the Curie stuff, just tell me how many nuclei, how many radioactive nuclei do I have in the sample. So I put in the decay rate, and then I put in the lifetime, and remember the lifetime here looks funny, it looks like a conversion factor because it's 1.0010 to the 6 seconds, but that's just by chance. And so I multiplied by the lifetime, and I ended up with 3.710 to the 13, and I know when things have the same number, 3.7, 3.7, you see that and you think there's some kind of a reason, but it's just by coincidence. Anyway, this is the number of iodine 131 nuclei in the sample we're talking about. So this sample, which is, physiologically harmful, is 37 trillion iodine 131 nuclei. And then what we can do is we can use the molar mass, 131 grams per mole, and what we get is a mass, and it turns out its mass is only 8.1 nanograms. So what do you think? Can you see a sample of 8 nanograms? I don't think so. This is really, really tiny. So one of the most important concepts to be aware of with all these nuclear physics problems is there's a lot of atoms in samples, right? There's just an enormous number of atoms. This is probably something you can't observe, but it's got, 37 trillion atoms inside of it. So, or you can't observe without some kind of instrumentation to assist. Okay, so that's risky. And then, when I finished this problem, I was a little not completely satisfied because the problem was billed as a radiation dose problem, but they never asked us about the radiation dose. So I had to add part D. So on part D, I said find the dose, and for that, I went in and calculated Q. So I looked up the iodine 131, and I looked up the xenon 131, and I did the Baig decay reaction, and if you go back and, very quickly, go back and look at that, what it's saying here is that I don't want to include the mass of any electrons with beta minus decay, because by including the mass of the xenon, I will have already taken that electron's mass into account. All right. So there we are, and I did a Q value, and the Q value here was 0.984 MeV. So that's what I got for Q. Now, what I'm thinking of in terms of dose is, let's imagine all of these decays happen, and they all take place in the thyroid gland. So the thyroid ends up taking the full dose of all of these decays, and so I need to calculate the total energy of decay. And so I took the 3.710 to the 13, that's how many nuclei, radioactive nuclei we came up with. Now this is the energy that's released each time it decays, that's a period, not a comma, period, right there. And then I converted those MeV back into joules, and it says by the time all of these have decayed, and remember this is going to take weeks and weeks and weeks, is what we saw. So it's going to take weeks and weeks until most of this has decayed. But during that time, the thyroid would end up absorbing 5.83 joules. These are electrons coming out, and the electrons are going to travel short distances. That means that the thyroid is large enough, it will slow down most of these electrons, and all of the energy from the electrons will be absorbed into the thyroid. Now, on the other hand, there are neutrinos coming out. So this is actually one of the places where physics gets it right. When we talk about radioactive decay, we talk about neutrinos, and chemists seem to shy away from that. When I look at chemistry textbooks, they I don't see a lot of mention of neutrinos. But the neutrinos that are coming out are going to carry away probably half or more of the energy. So that's a factor of 2 in our favor. It says that even though this much energy is released, probably half of that just flies out with the neutrinos, and the neutrinos don't interact very well with anything, and so it's very unlikely any of them would react with the thyroid, or the portion that react would be, it could be none. Neutrinos really don't react very well with things. And so maybe this number is only half as large. In any case, I looked up the mass of a thyroid, and it says, you know, a typical adult person, thyroid might be 15 to 20 grams, so I took the 20 gram size, and the radiation dose, officially, is finding how much energy of radiation is there in the sample divided by the mass of the material in which that radiation energy release takes place. And so if it's this much energy of ionization from the high energy electrons divided by 20 grams, I ended up with 292 gray. Now that's a really, really high dose. So yeah, it's not surprising that you know, several hundred gray, 300 gray or so, could destroy the tissue. And again, remember that all the iodine got concentrated, so other parts of the body are going to have basically no dose from ingesting the iodine 131. It's, you know, it's all going to end up going into the thyroid. Now, if the neutrinos carry off half that energy, then, you know, we're down to like 150. But 150 gray would still be a pretty large dose, and yeah, that could certainly take out some tissue, some physiologic tissue. All right, I think that's it. Let me see if I've got more here. Nope. The next, so we're going to take a break right there, and because I think it's time, and then we'll come back. So in the second lecture today, we will come back and look at chapters 43 and 44 and look at some homework problems there. I hope this helps. I hope this is useful. Sometimes talking about these homework problems make them more real, and then seeing how they're set up is pretty handy. If you guys have questions, stop by office hours and we'll get those looked at.